take Q an equivalent martingale measure. That is, Q is equivalent to P, and S is a martingale under Q. We want to describe the set of equivalent martingale measures, and we shall do so by describing this general equivalent martingale measure in terms of its values at the elements of omega. We shall find all Q x1, x2 for the pair x1, x2 in omega. First, notice that since omega is finite and P is positive, on every element of omega, it holds that Q and P are equivalent if and only if Q of the pair x1, x2 is positive for every pair x1, x2 in omega. We've assumed, of course, that Q is equivalent to P, and therefore we can define positive constants Q1 by Q at 1, 1, excluding the curly brackets here, plus Q1, 2, plus Q1, 3. So summing with 1 in the first variable and over all possibilities in the second variable. And similarly, Q2, summing with Q in the first variable and all possibilities in the second variable, which is just in this case 1 and 2. And further, we can kind of split this probability measure down even more by defining Qij to be equal to, so I should write this just in a more general way, Qij to be equal to Qij divided by Qi. This is for I in 1, 2, and j in 1, 2, or 3, but only 1, 2, or 3 in the case that I is 1, 1 and 2 in the case that I is 2. So how to write this in notation, but j in 1, 2, 3, if I is equal to 1, in 1, 2, if I is equal to 2. So just defining of all the possibilities that we have. For these constants, we can characterize the measure Q of general x1, x2 as equal to Q x1 multiplied by Q x1, x2, which is of course a form that P has. And the reason for doing all that is showing that if we have P of this particular form, then because Q is an equivalent measure to P, it's also possible to define Q in that form. What the additional conditions on P also hold for Q, so that's Qx1 and Qx1, x2 are in the interval 0, 1. They are positive but not equal to 1. and satisfy the sum over the possibilities for x1, qx1 is equal to 1, the sum over the second variable when the first is fixed at 1 is equal to 1, and in exactly the same way as we just had above, the sum over the second variable 1, 2, that's disappeared, when the first variable is fixed to be 2 is also equal to 1, just by how we've defined our q ij's. So q has now a similar expression to p, and we can calculate these constant values and it will fully define any equivalent martingale measure. Since S is a martingale under Q, because Q is an equivalent martingale measure, we have that the expectation under Q of S1 is equal to 100. The expectation under Q of S2, given the event that S1 is equal to 100, S1 is equal to 200, is equal to 200, and expectation under Q of S2, given that S1 is equal to 50, is equal to 50. All of these just calculated using the values of possible values of S0, S1, S2 given in the statement of the question. This first, for example, coming because we have a martingale, so that's conditioning, although it's not given here explicitly, but conditioning on the trivial sigma algebra, so the value of S0. So these just from the martingale property and the values of S0, S1, S2 as given in the question, nothing to do with the probability measure P as of yet. So using our Qx1 and Qx1x2 from above, we can use these three results from the fact that Q is a martingale measure to write three systems of equations, of linear equations, to help us deduce these constants for Q. The first is that Q1 plus Q2 is equal to 1, and 50Q1 plus 200Q2 is equal to 100, which uses the fact that the expectation of S1 is equal to 100 under Q. The second is that Q21 plus Q22 is equal to 1. That's again just from the definition of Q21 and Q22. They are defined to together fill the whole of omega. And 100 Q21 plus 300 Q22, this is summing over the possible values of S2, is equal to 200. That from the second equality gathered from Q being a martingale measure. And third system of equations, Q11 plus Q12 plus Q13 is equal 1, and 30Q11 plus 50Q12 plus 70Q13 equals 50. And so we can just solve these systems of equations in order to deduce the values of the Qij's. Systems 1 and 2, that they both have two equations for two unknowns. So as long as those equations aren't versions of one another, then we should be able to get those unknowns explicitly, and in fact we can. Solving them gives that Q1 is equal to 2/3, Q2 is equal to 1/3, Q21 is equal to 1/2, and Q22 is also equal to 1/2. On the other hand, the system 3 has two equations for 3 unknowns, so we would expect that one of those unknowns could be some arbitrary value. Which we shall denote by rho. So we get Q11 equal rho, Q12 equal 1 minus 2 rho, and Q13 equal to rho, so also equal to Q11, where rho takes possible values between 0 and 1/2. It obviously couldn't be larger than 1/2 because then Q12 would be less than 1. This, what we have then, just from the basic assumption that Q is an equivalent, we've just taken Q to be an equivalent martingale measure, nothing else. We have fully characterized it in terms of the Q's. So there isn't just one equivalent martingale measure, there's a set of equivalent martingale measures. Measures indexed by some value rho in between 0.5, so it's measures such that, well, rho is in 0.5, Q can be expressed for x1 and x2 as a product of qx1, qx1, x2, and the values of these qx1s and x2s are as above. 2/3, Q2 is 1/3, Q11 equals Q13 equals rho, and Q12 equals 1 minus 2 rho, Q21 equals Q22 equals 1/2. That's the set of equivalent martingale measures that we needed to find. Now in the second part of this exercise we want to explicitly construct a hedging portfolio for a particular European call option. I just want to remind you that hedging portfolio, so it's a self-financing trading strategy that's also replicated. We're going to get a useful form of this, of a self-financing even without first assuming replicating trading strategy, just to remind you, from in terms of the difference of its value process from one step to the other, and the difference of the value of the risky asset from one step to the other. This is what's called delta hedging. Just using the definition of the value process, Vt as phi t plus 1 of phi Bt St, which, since phi is self-replicating, is equal to phi t times Bt St, and at the time step before, we can obtain an equation for phi t multiplied by the difference of these two from one time step to the next as the value of Vt. This is delta Vt, so value of Vt minus Vt1, t minus 1. So since we're currently in a situation where Bt is equal to 1, right, the non-risky asset is not increasing, the phi t multiplied by Bt minus, or alpha t in this case, or beta t, sorry, multiplied by Bt minus beta t times Bt minus 1, well, it just all is equal to 1, and we get phi t equals Vt minus Vt minus 1 over St minus St minus 1. This is just for phi, a self-replicating trading strategy. But we also want that, because we're looking for a hedging portfolio, we want that phi is replicating. I realise I just said that self-replicating, I meant self-financing. We want also that phi is replicating, right? That's what allows us to define a hedging strategy. And there's a lemma in the lecture notes that says that we have a replicating strategy if and only if the value of that strategy follows the price process of the asset, right? This is the price process is uniquely determined by the value of any replicating strategy. So what we shall do is calculate the price process of the asset that we have. From that, deduce the value of the any replicating strategy, which is the same. It's the same process. And then from this equation that we've just described, we can deduce then the actual replicating strategy itself, which will be our hedging strategy. So the option we're interested in is the European call option, S2 minus capital K plus, okay, it's a strike price in between 70 and 300. So since we know the values of S2, we can see that the payoff from C is non-zero, because of course it's already non-negative, if and only if S1 is equal to 200, because in that case S2 can increase to either 200 or 100, and it's possible for the payoff of C to be positive. If S1 were to equal 50, then S2 could have maximum value 70, and so the payoff of C would be 0. Then the value of the call option is given by 300 minus K in the case that S2 is equal to 300, 100 minus K plus, of course, depends on K, in the case that S2 is equal to 100. From that we can go back a time step and deduce the price of the risky asset at time 1, which is equal to the value of the replicating strategy. It's the expectation of S2, sorry, given S1, given that we know that we've at least gone up to this step. So this should be conditional here on the event that S1 is equal to 200, because that's the case we're talking about when we have this possible positive value. Right? And that expectation, well, we calculated that this probability is split evenly between the two, so this expectation is 1/2 300 minus K plus 1/2 100 minus K plus. And then at time step 0, we just want the expectation of S2 given the trivial sigma algebra, and we calculated this probability in the first part of the question to be 1/3 under our equivalent Monte Carlo measure. So we get 1/6 300 minus K plus 1/2 100 minus K plus. This is the price process of the asset, but it's also the value of any hedging strategy or replicating strategy. So now we can calculate our phi using this characterization in terms of V and S. So I just realized I made a notation mistake. Obviously we're using the notation that we have been using. That would be alpha for this self-replicating strategy there, not phi. Phi is the vector. So we can calculate this at time 1 and time 2. Alpha 1 is 1/2 minus 1/6. The difference is then between the value at time 1 and the value at time 0, which is just the same thing. That's why we can take those guys out, the half and the 6th. And we're left with the difference between 300 minus k and 100 minus k plus, which is the value of the option at time 2, and depending on what value S2 takes. And cancelling these out gives us a value of 200 minus k over 150 on the event that k is less than or equal 100, and 300 minus k divided by 300 on the event that k is greater than 100. In a similar way, we can calculate alpha 2. So we get on the left hand side 1/2 multiplied by 300 minus k, minus the half here, leaves us a half, minus the half 100 minus k plus, divided by, what's the value of S2? It's 300, minus the value of S1, which of course is 200. All of this is on the event that S1 is equal to 200. Plus then a half, and this time the tables are turned. 100 minus k plus, minus a half 100 minus k plus, minus the half 300 minus k, over the value of S2 minus the value of S1. That's 100 minus 200 now, because it's decreased in value. So that 100 minus 200 becomes minus 100, moving that minus sign out, and combining these gives us on the top 300 minus k, minus 100 minus k plus, on the bottom 100 times by 2, because we've got that half in there, so 200. All of this should be here as well, on the event that S1 is equal to 200. And finally we can write this as well as indicator of S1 equal to 200. Now also k being between 70 and 100. In that case, the k's cancel on top, we get 200 over 200, so it's just equal to 1. And on the other hand, if k is greater than 100, then the 100 minus k plus goes to 0, and we get just 300 minus k over 200. So let's multiply by the indicator that S1 is equal to 200, and k is greater than 100. And so we have our hedging strategy.